So this is just a brief review of how we solve second-order differential equations having constant coefficients, and particularly the non-homogeneous situation when we have what's known as a forcing term on the right-hand side. So the first step is to solve the corresponding homogeneous equation, ay double prime plus by prime plus cy equals 0. And the way we do this is we actually solve the corresponding characteristic equation, which is ar squared plus br plus c equals 0. And we may need to factor or use the quadratic formula or whatever, but we get two roots, r1 and r2. Now the simplest case is if the roots are not equal, in what like r1 might be 2 and r2 might be 3, and we can simply write down the fundamental solution to the homogeneous as c1 e to the r1t plus c2 e to the r2t. This is the easiest situation. The next case would be when we have complex solutions to the characteristic equation. In this case, let's say our roots are a plus bi and a minus bi. These are what's known as complex conjugates of one another. We just switch the plus sign to the minus sign over here. This isn't too bad either. The solution is always going to be a constant, e to the at, a is the real part, the stuff without I, times cosine bt plus c2 e to the at plus sine of bt. This is always going to be the case if you have complex values for r1 and r2. The third case is a little bit more delicate. If we have roots r1 and r2 that are the same, we don't want to just write down c1 e to the r1t, c2 e to the r1t again, because that's really just the same solution. So the method of reduction of order says that we can simply get the second solution in our fundamental solution set by taking e to the r1t and multiplying it by t. That's always going to be the case for a second order equation. So let's take a look at an example. Y double prime plus 4y prime plus 5y equals 0. So this is homogeneous. The characteristic equation is r squared plus 4r to the plus 4r plus 5 equals 0. And if we solve for r, this is one of those situations where we need to use the quadratic formula. So we have minus b plus or minus the square root of b squared minus 4ac all over 2a. So this is minus 4 plus or minus. Under the square root, we're going to have 16 minus 20, which is minus 4. All of this will be divided by 2. Now the square root of minus 4 is going to be imaginary, so let's just go over here. The square root of minus 4 would be the square root of 4 times the square root of negative 1. The square root of 4 is 2, so this will be just 2i. So that means that r will be minus 4 plus or minus 2i over 2, and we can factor the 2's out of the numerator and cancel, so we get minus 2 plus or minus I. So in this case, a is negative 2, b is 1, so the fundamental solution would be e to the minus 2t cosine 1t, or just t, plus c2 e to the minus 2t sine of 1t, or just t. So this would be the fundamental solution in the case of this second order homogeneous differential equation. Now let's suppose we have something a little bit different, y double prime minus 4y prime plus 4y equals 0. In this case, our characteristic polynomial is r squared minus 4r plus 4 equals 0. This factors as r minus 2 quantity squared equals 0. So in this case, we have a repeated real root. r1 and r2 are the same. So r is 2. Our first solution is e to the 2t. And then our second solution is just t times that, t e to the 2t. That's the idea of reduction of order. So our solution would be c1 e to the 2t plus c2 t e to the 2t. And of course, if we had initial values, we could determine what those constants are. Let's switch to the non-homogeneous case now. When we have a function on the right-hand side, we sometimes call this a forcing function. One way to solve this equation, it works in many situations, is to find a particular solution using the method of undetermined coefficients. So here's an example. Suppose our forcing term is the cosine term, is a cosine. we might try our particular solution, y sub p, to take the form a cosine t plus b sine t. If our forcing term on the right side was quadratic, 1 plus t squared, we might try letting y be at squared plus bt plus c. If the right function on the right side was e to the 2t, we might try function of the form y equals e to the 2t. So the idea is that you try to choose your particular solution so it sort of fits the form of what you have on the right-hand side, and that comes down to solving for these coefficients, be it capital A and capital B, little a, little b, little c, or capital A down here, and that's why we call this the method of undetermined coefficients. So let's take a look at an example. Y double prime minus 4y prime plus 4y equals sine of t minus cosine of t, subject to the initial condition y of 0 is 0, y prime of 0 is 1. So because we have a sine and cosine term on the right-hand side, we'll make a guess for our particular solution to be a cosine t plus b sine t. Now we're going to have to go through the tedious task of plugging this y into the left-hand side and get the coefficients to match up with what we have here. So we have to calculate y prime, which would be minus a sine t plus b cosine t. That's the first derivative. And then we have to take the second derivative, which would be minus a cosine t minus b sine t. Again, I'm using the fact that the derivative of the cosine is minus the sine. Then we got to take this y prime, and this y double prime and solve it into this. This is a royal pain. So I've done it over here. So I have y double prime, which is minus a cosine t minus b sine t, minus 4 times y prime, which was minus a sine t plus b cosine t, plus 4 times y, which was a cosine t plus b sine t. So I'm going to do some expanding here. I get minus a cosine t minus b sine t, that's this part, and then minus 4 times minus a sine t is 4a sine t, minus 4 times b cosine t is minus 4b cosine t, and then I have my 4a cosine t and my 4b sine t. Now what I'm going to do is I'm going to group all the sine terms together and all the cosine terms together looking at this. So the sine terms, I've got minus b right here, I've got a 4a right there, and I've got a 4b right there. So I have minus b plus 4a plus 4b. If I look at the cosine terms, I have a minus a, I have a minus 4b, and I have a 4a. So this is what I have in terms of the sines and the cosine terms. And what I want is I want the capital A and the capital B to work in such a way so that I get sine of t minus cosine of t. That means the coefficient of sine of t, which is minus b plus 4a plus 4b, has to match up to 1 because I had a sine t above. And the coefficient of cosine, minus a minus 4b plus 4a, has to match up to minus 1. And again, the 1 and the minus 1 are coming from the fact that the coefficients of sine and cosine here are 1 and negative 1 respectively. This is a system of equations, two equations and two unknowns. There's various methods to solve it using matrices, substitution. I simply did it on Wolfram alpha, and I got A equals 1/25 and B equals 7/25. So that means if we go back to the original differential equation, the solution is the fundamental solution to the homogeneous, c1 e to the 2t plus c2 t e to the 2t. And then I want to add in that particular solution I just found on the previous page. 1/25 cosine t plus 7/25 sine t. So this is the general solution to the non-homogeneous. The general solution to the non-homogeneous is the general solution to the homogeneous plus a particular solution to the non-homogeneous. Try saying that quickly. Okay, so we now need to use our initial conditions to figure out what C1 and C2 are in this case. Now I said that y of 0 is 0, so if I plug 0 in up here, I get C1, because e to the 0 will be 1, C2, but then when I plug 0 into this, it's going to go away because of that t term. Plug 0 into the cosine, I get 1, so I'll have a 1/25. 0 into the sine of t, it goes away. So 0 equals c1 plus 1/25. Therefore, c1 equals minus 1/25. I'm going to go and plug that into y prime when I take y prime in a moment. So when I substitute minus 1/25 back here, if I take the derivative of this, I'll get e to the 2t times t. To take the derivative of this, I have to use the product rule. Keep in mind that c2 is a constant, so I'll have derivative of t, which is 1, e to the 2t, plus c2t, e to the 2t times 2. So I use the chain rule to get this term right here. I use the product rule to get this entire quantity right here. I applied the product rule to that up there. Now I need to take the derivative of that, which is minus 1/25 sine t, and then the derivative of this is 7/25 cosine t. So let's plug 0 in for t. This will become 1, and I'll have 2 times minus 1/25, which will give me minus 2/25. I'll get a 1 here because e to the 0 will be 1. When I plug 0 in here, it just goes away. When I plug 0 in here, the sine of 0, it goes away. And when I plug 0 in here for t, I get 7/25 times 1. So I have 1, that was y prime of 0, equals minus 2/25 plus c2 plus 7/25. And if you do just a little arithmetic, you can see that c2 is 4/5. So the final solution to the non-homogeneous initial value problem is y equals minus 1/25, that was c1, e to the 2t, plus c2, 4/5 t e to the 2t, plus our solution to the non-homogeneous, which is 1/25 cosine t plus 7/5 sine t. One thing I should point out is that sometimes it's common that people will try to determine what c1 and c2 are before they find the solution to the particular, and you can't do that. You always have to figure out the solution to the particular and then find the values of c1 and c2 because their values depend upon what we get over here. So that's an overview of how we solve a second-order homogeneous and non-homogeneous differential equation using the method of undetermined coefficients.